চাই? ম্যাচেস।
একটু জুম করে নাও না পোডিয়াম। उत्तम ये लाइटर है देवता लाइटर আমাদের অফিস থেকে নিচ্ছে
So we are okay. Before I say that, so good morning everyone. So this is the opening inauguration session of the symposium on texture in materials. This is a SPARC phase 3 symposium. Actually this is the second of the conferences that we are doing. Initially 1.5 years back, when the SPARC just started, this project just started, we did a very 2 weeks of workshop on grain boundary and triple junctions, right? Texture, grain boundary and triple junctions. So this is the second in this series and the last one for this project, but we will keep on doing something like this in the field of texture. Last time, if you remember, along with Professor David Field, Professor Sinisa Mezorovic and Professor Shoumik Banerjee came from Washington State University, Pullman, USA. And this time we again have our esteemed dignitary Professor David P. Field with us, and I would like to welcome you, Professor, with an applaud. So in this inauguration ceremony, I would just like to say that this particular symposium is made in context of understanding the basic fundamental of mechanical and physical metallurgy aspect, which is called the texture. Many of you have very less idea about what is texture, but if you look into the modernization of the industries, and if you look into how the classical metallurgy has been involved into modern and quantitative metallurgy, you must realize that quantification of every aspect, including mechanical properties, electrical properties, magnetic properties, like them, the quantification of metallurgical properties are very important. The quantification of the microstructure is very important. The quantification of how the grains in the microstructures are oriented is very crucial, because we know that any material, and I give an example out of it. For example, the most isotropic polycrystalline material, which is body centered cubic, it can be manipulated or it can be engineered to produce a sheet of a body centered cubic ferritic material or a dual phase material to have its strongest direction or the closest pack direction, which is 111, along a certain direction. Say for example, we can do that parallel to the thickness of the sheet, and if it is possible, and which is called the gamma fiber basically, and if it is possible, then we have very good deep drawing ability. We can make larger deep drawn cups from the BCC, because it will have the highest anisotropy in this case. Like that, we know that there are Gauss texture, which is basically grained oriented silicon steel, right, and that is used for transformers because it has the lowest, of the energy dissipation during magnetization and demagnetization. So, it has the smallest area under the hysteresis loop, and the grain oriented silicon steel, the Gauss, and coincidentally the researcher who invented it is also Professor Gauss. The you have is used in transformers, right. So, without making much of a speech, I would like to say that this particular symposium has been organized in the honor of Professor David P. Field, who has come to IIT Kharagpur and have graced us with his presence, his lectures. Fortunately, and he is actually presently teaching my texture course for 1 week now, and he is going to teach in the next week too, and that's I am very happy that my students are getting international exposure. So, as you know, there must be I don't need to give any introduction of Professor Field. He is one of the renowned professor in mechanical and physical metallurgy. He has done a pioneer job in developing of the quantitative microscopy using electron backscatter diffraction in an SEM. He has lots of pioneering work. Recent works on of his is like detailed fundamental understanding of triple junctions. So, he is presently and for a long time is also the chief editor of the journal Materials Characterization. So, apart from this, in this symposium we have presentation by Professor Satyam Suhas, who is from IISc, from Professor K.S. Suresh, Shantaram Suresh from IIT Roorkee, Professor Shivayan Roy from Material Science Center, Professor Indradev Samasdar from IIT Bombay, then Professor Debalay Chakrabarty from Professor Sumantra Mandal, Professor Nilesh Gurao from IIT Kanpur, and Professor M. Arul Kumar from IIIT Kanchipuram, who just have come to India from Los Alamos National Laboratory. So, this is all the introduction of the entire thing, and I would like to call Professor Field and Professor Sampaij, who Professor Sampaij and Professor Field is also actually the organizer, along with Professor Sinisa and Shomik Banerjee. So, I would like to call in the dais so that you can light the lamp and inaugurate our session. Okay, please keep it, and then we will, while the session is going on, it will be distributed silently. Mombati.
Just 4 is there, maybe can manageable make so that's what's.
So with this lighting of the lamp, let us start our session. I'm not asking Shampa madam or Professor Field to say anything, but let us start with our first session where Professor Field is going to speak on
Talk about
crystallography and introduce us to texture.
you tell us, especially me, I will repeat whatever you said just now. So that doesn't make sense to maybe Professor Field can say something.
So before the presentation starts, I would like to welcome Professor Field. I will ask Professor Sampais to welcome him with a bouquet. And I also welcome Professor Sampais with this bouquet.
And who is going to welcome him?
I'm welcome. I'm the one who is the host.
I will. He is the main person here. He is supposed to be welcome.
Okay. Thank you, Somjit and also Shampa. And thank you everybody for being here today. It's a pleasure to be able to come back and see a lot of people who were here last time I was here. The presentation I'm giving is very introductory in nature, and part of it is very similar to what we talked about last time I was here as far as the crystallography and my focus on EBSD, and so I will talk about electron diffraction in connection with crystallography. But this one I was asked to also introduce texture, and I have this caveat here on the end of the slides that say all of these slides are not mine. Some of them I've taken from colleagues who I've worked with over the years. Sometimes I don't even know whose slide is whose anymore, so I just say I acknowledge these people who I've worked with. So it's always good to acknowledge people who are doing the work. All right, so texture analysis. If we say what is texture, it's kind of a funny word because texture, when we think of it in the world, we think of, as a surface rough, right? That's the texture of the surface. If you Google just the word texture, you probably won't learn about crystallographic texture, right? You'll see other things. But it comes from this Latin root of textura, which is weave, which means a couple of things, but the definition I like is the arrangement or manner of union of the particles of a body or substance. Now this was first introduced actually by geologists, and geologists use the term texture for what we would call microstructure. And for the word texture, when we're talking about crystallographic texture and preferred orientations, typically geologists use the word fabric. Okay, so another thing that's a little bit different than typical. Metallurgists, we adopted the word texture over 100 years ago, so in the early part of the 20th century, we started using the word texture as metallurgists to define preferred orientation, because it was noticed that during processing or casting that there would be specific crystallographic directions that lined up. So that's when the word texture started coming into play. So if we say what is texture, and we just draw some pictures are always good. We say here is an arrangement of crystallites, and on the right side, these are all kind of these little unit cells in each grain are kind of oriented all the same, right? Very, very similar orientations. If we did an orientation map where the colors represented orientation, they would be all similar color, like this blue color shown here. So that would be considered to be a strong texture. You would have a strong preferred orientation. That's the phrase we typically will use, is preferred orientation. If you have crystallites in grains, the lattice orientation that's randomly oriented, so changing from one to another and kind of all with the same probability, then we would consider that to be a random texture or a uniform texture. Sometimes you'll hear people argue about the difference between a uniform texture and a random texture. I don't argue about it. To me, they're about the same, and so I don't worry about it, right? But sometimes the purists, especially the mathematicians, will argue about difference between random and uniform. But to me, it's random texture, uniform texture. All right, there's another term you'll hear called microtexture. Microtexture is a little bit more screwed up with microtexture because it was first used to describe grain boundary character distributions. People started saying instead of grain boundary texture, they would call it microtexture. Say here's the grain boundaries that are used, or the distribution of crystal, grain boundary planes and crystallite lattice orientations on either side, or the misorientation distribution, we'll call that microtexture. But then other people use it and say this is for orientation gradients within grains, or this shows orientation gradients over many grains, or this shows a local colony structure in titanium, something like this. So I asked ChatGPT, right? Anytime I don't know something, I ask ChatGPT. And ChatGPT was very political in nature and gave me all of the answers, right? It says microtexture is this, all of these things. And if you go to the next page, it says typical features of microtexture, and then it lists all of them again, right? So microtexture can be used for all of these. I would prefer when describing some specific distributions that you use local texture. If you're talking about gradients within a grain or within several grains, or use grain boundary texture or grain boundary character distribution, something like this. But you'll hear the word microtexture a lot. It's become very common in the literature. And again, people mean different things when they say microtexture. So you just have to read between the lines and see what they're talking about. Okay, so who cares, right? That's always the question. Who cares? I always tell my students, if you're to describe your research to somebody, right? Do your 3-minute thesis or do your elevator pitch, whatever we talk about, whatever you want to call it. I always say there's 3 things you have to tell them. You have to say, why does anybody care about this, right? What's the problem, right? So in texture, it's, how can we form materials better? How can we waste less material during deep drawing or something like that, right? So here's a problem. Here's why I care, right? What your particular research is. So maybe you're looking at mechanisms of defects in orientation, evolution, something like this, right? What's your specific problem? and then what have you learned quickly, right? So those three things. So that's why I like 3-minute thesis, because you can spend about 1 minute on each of those things to say, here's what the answer is. So that's what I always start with. Who cares? So why does it matter? So typically anisotropy is the issue. And if you're talking about wood, we understand very well that if you have an orientation where the grains are going through the thin direction, it's easy to break that wood. Right? If I'm doing a karate demonstration, I want to use this board instead of this board because I don't know karate, right? So I just use one that can break easy. Same thing occurs in crystals where we have different strengths, different stiffness, different properties in different directions. Now I have a bias towards mechanical properties, so typically when I talk about properties, I'm talking about mechanical properties. But the same would be true of magnetic properties or optical properties or electronic properties, right? Conduction, these kind of things. The same is true of all properties that we're talking about. So we have an anisotropy that exists. Now texture then is important because it controls what those properties are. So if we have a very weak texture versus a very strong texture, we'll have different anisotropy controlling those properties. All right, so why do we have texture? Well, it's through processing, like I mentioned. And it's pretty much any type of processing. If we're talking about metals, if you're rolling, forging, extruding, any type of deformation, you're going to develop a texture that gives you a preferred orientation for that specific type of deformation. Now, it's not always straightforward, right? We think of slip planes and how this works, and the slip planes are lining up in kind of the standard Schmid example with the zinc single crystal, and you pull the rod and the planes rotate, and you can see them rotate with the slip lines. And sometimes that explains everything. But sometimes if you sprinkle in a little bit of extra alloying element, even a few % of something, then things behave differently, right? Then it's not a Schmid behavior, then you get dislocations pinned or whatever by the particles or the solutes, and you get a different type of texture evolution. So there's a lot of very unanswered questions, a lot of specific details that we know about, but also a lot of unanswered questions on how exactly texture evolves in specific alloys, chemical composition dependence, as well as geometric dependence. But it doesn't matter how we form materials, we get texture that develops. Even if you're doing films, sputtering a film, you can get a very thin film. For example, if we're doing an FCC material, then surface energy minimization will dominate the structure, and we'll have 1-1-1 in the surface plane. Right? We'll have a 1-1-1 texture that will be maybe randomly distributed within the plane. If we increase the thickness of that a little bit, then strain energy starts to dominate, and we get 100 in the plane. So all those 1-1-1 grains, if you anneal them a little bit, they'll all switch over to 100. Right? So we kind of know how to make textures and how to control textures. There's a lot of thermodynamics involved as far as energy minimization, but we've kind of developed this base of where we know how to control texture in a lot of different materials, a lot of processing. Now again, if we sprinkle some other magic dust into something, then maybe the answer is different, right? So we have to include all of that. This, I wasn't necessarily going to show this, but I like this video because in my state, there's a company called Pacific Aerospace and Electronics, and they do explosive bonding. So they get all these plates, put all the aluminum nitrate fuel oil, ANFO, on there, blow it up, and you have all these plates that join together. And I have a student who did his PhD in this, and so the texture that evolves along that interface is very dependent on how much ANFO charge there is and on what the spacing is between the plates before you slam them together. So you can control that very nicely, the texture that occurs at the interface, which is kind of interesting because it's just blowing stuff up, right? So I'll let you see this last one. This is 2 pipes being deformed together, right? So the outer pipe is being blown up onto the inner pipe. This one's nice because at the end it does slow motion, so you can see a nice slow motion explosion. This doesn't have much to do with texture. It's mostly for my own amusement because it cheers me up to see this. That explosion that you see first on the back there, that's a prime cord that goes, and that explodes, and then it causes the prime cords up to each individual canister to go. And it does that so that they all explode at the same time. Because if one explodes first, then it knocks the other one over to some other orientation, and it explodes, and it flies off into the forest, and you never find it, right? So that's how they do that. Anyway, so processing, any kind of processing creates some kind of texture, and we should figure out how we can control that. So what's the effects if we don't control the texture? What happens? And there's a lot of different things we could put in this list. I've just chosen a few that are texture-dependent properties. Certainly all the anisotropy and strength, stiffness, hardness, all these mechanical properties I told you I'm interested in. Earring and deep drawing, this is one of the most textbook examples of poor textures, right? So you roll out a material, you get a very non-uniform texture, you'll create these ears on the cup. But we know how to process to minimize those ears. This little cup that isn't seen as good, this one has 6 ears on it instead of only 4 ears, right? So we can do 6 ears, we can do 8 ears, depending on what kind of texture it develops. And then you get less and less earring height of those ears. So when you're trimming the part at the end, you have to waste less material, right? Or you have less material to recycle. So that's kind of the textbook example. Very ductility, fracture toughness, forming limits, residual stresses certainly are directional dependent. Elastic properties, which if you think of elastic properties and what the elastic modulus or that lattice phonon controls, it also is related to conductivity, right? So if we have difference in elastic moduli, then we have different conductivity along those directions as well. Molding difficulty, this comes from as you have directional solidification, if you have some thermal gradient in a mold, you get some orientation that's moving along here, and then all of a sudden you have another part of the mold where the thermal gradient is in another direction, then you'll have incompatibilities and potential for shrinking of pores that form where that joint is. So some casting issues. And then corrosion, stress corrosion, a lot of other challenges that we can talk about that are a function of texture. So that's why we care about texture, right? It gives anisotropy in the material and causes some issues in performance of the component. All right, so let's talk about definitions a little bit. We talk about an orientation of a crystallite. This is just a rotation that will rotate the coordinate frame fixed to the crystal lattice into a coordinate frame that is defined by the specimen. Okay. Now in material science and texture analysis, we always rotate the specimen coordinate frame into the crystal coordinate frame. Right? So if we're trying to define the orientation of this desk with respect to the room, instead of just rotating this desk to the coordinate frame of the room, we would rotate the room to the coordinate frame of the desk, right? Physicists do it differently. They call that the active formulation. We use the passive formulation. So we're rotating the specimen coordinate frame or the external reference frame into the coordinate frame of the crystal. And that's just, we don't have to do that. That's just convention that's built up. So all of the conventions, you know, Bunga, Euler angles, Rho, Cox, that's all I think of for now. Seems like I missed one though. Anyway, all of those use the same kind of conventions, right? All the passive frame. If we talk about a misorientation, right? A misorientation will take the rotation from one crystallite, right? The orientation of this one, rotated into coincidence of its neighboring crystallite, or into coincidence with some other crystallite somewhere else. That's called the misorientation between those. Now the orientation and the misorientation require 3 parameters, and I think somebody's going to talk about this later. Require 3 parameters. Sometimes we use Euler angles to define that parameterization. But you could also use an axis and an angle of rotation, right? So there's a common axis between two coordinate frames and some angle. Okay, so any of these you can use. All right, orientations and misorientations. So how do we measure these things? Mostly we measure them with diffraction techniques. So bulk measurements done with X-rays or neutrons, typically. Sometimes you can do them with electrons, particularly in TEM. But we're measuring many crystallites at the same time, coming up with overall distributions. You can do spatially specific measurements, looking at a single crystallite. You can do this in a synchrotron sometime with diffraction contrast tomography, or DCT they call that, or sometimes you can do it in the lab with a micro CT system. TEM, Kikuchi or spot patterns. There's polarized light techniques where you can kind of measure orientations of crystals, causal patterns, channeling patterns or electron channeling patterns, or sometimes they're called rocking curves, or electron backscatter diffraction, right? To measure these things. Now like I said, I've used electron backscatter diffraction for a long time, and I put all my notes in basically in that frame set. So I'm going to talk about EBSD a lot as we talk about some of these things. All right, traditional measurement techniques, which other people are going to talk about, but just generally, if you set your incident radiation and your detector position at the Bragg angle, which I haven't defined yet, but it's set them at the Bragg angle, and then you rotate your specimen, you can find out what's the intensity of diffraction of the planes that cause that diffraction at that position. And you rotate around to all these different positions and say, okay, these 3 red grains, they contribute to this spot, and these 4 green grains contribute to this spot. And you do that for the entire space of a stereographic projection, which I think is coming next that you hear about. And you come up with a texture plot, or a pole plot we call them, or a pole figure. This is just kind of for completeness. That talks about different resolutions and advantages and disadvantages of some of these techniques, and I'm going to skip through this because I was asked to talk about crystallography a little bit. So we're going to go into crystallography just as is needed for what we talk about in texture. So it's not in-depth crystallography. I'm not a crystallographer. I don't know a whole lot of group theory, these kind of things. But you know, if there's a crystallography class, you'll learn a lot of stuff that you won't learn from me. That's what I'm saying. Okay, so very simple. Crystal, definition of a crystal. You have a set of unit cells, and those unit cells can repeat over space, filling all space. You have these lattice vectors, and those lattice vectors, you continue to add and subtract those, and you can come to points of your lattice throughout all space. And that's in 3 dimensions, of course. We define the lattice by lattice constants or lattice parameters. So we have A, B, C, which are the lengths of the vectors. And we have alpha, beta, gamma, which are the angles between the vectors. Right, so those 6 parameters, A, B, C, alpha, beta, gamma, define your crystal. We have a set of planes that can be defined within the lattice. We have a set of directions that can be defined, and these zone axes. So if we talk about directions, if you think of this as a X, Y, Z coordinate frame, just a orthonormal Cartesian coordinate frame, these directions of the vector, or the directions of the crystal, are just in the directions of a vector. So if we're in the X direction, we have one unit in X, 0 units in Y, 0 units in Z, so 100 is the direction there, right? These are called Miller indices. We call these UVW for specific Miller indices. So we have 100 here, 010 here, which would be aligned with a Y-axis or a E-hat2 axis in your crystal. And then all the other directions, right? 111 is the body diagonal. If we go to trigonal or hexagonal, we add a 4th redundant value because we use 3 parameters in the plane that are lined up with the, the obvious directions in the hexagonal coordinate system. Okay? So a direction along this position, for example, and I think I have this in a slide, direction along here, right, we're going -1 in the A direction, we're going half in the A3 direction, and half in the A2 direction as we project that onto those directions. And so we would have a direction that would be a 1 or a half, something like this, 1 along here and half along the other directions. And then we usually don't keep those fractions. We will add we will change the fraction like we did here, where you have 1, 1, and 1/2 positions. We'll change that so they're all integers. We just take the least common denominator, multiply them all, and so instead of 1, 1/2, it becomes 2, 2, 1. We do the same thing in hexagonal. Okay, but then we have these 4 indices, and the third index is redundant. It's just minus u plus v. Okay. For planes, we call these HKLs. Families, we have these curly braces on the planes. The families, we have the pointy braces, right? So HKL is a specific plane. These are defined a little bit differently, where we use the intercepts of the unit cell, take the reciprocal of the intercept, and make that the value of the H, K, or L. Right, so this is along the x-axis, the y-axis, the z-axis, or the E1, E2, E3 axis. And so you take these intercepts, you create the indices. If we have a plane like this, like the 010 plane, we have a intercept along the y-axis and nothing along x or z, right? So that's an infinite intercept, and we take the reciprocal, it becomes 0, right? Okay, and then we can do the same thing in these hexagonal structures, and we'll get pyramidal planes like this one, or prismatic planes, or down on the bottom is the basal plane. And all of these correspond to what we can see in diffraction patterns. And we're going to try and describe how that happens, but the symmetry of the crystal is also seen in the symmetry of the patterns. Okay, that's the point of this slide. Okay, on d-spacing, just to make sure we're clear, so if we have a 010 plane, right? So this is an 010 plane, and they fall 1 lattice spacing apart from each other. Okay. If we have an 020 lattice spacing, then we take the reciprocal, and it's half of the lattice spacing. Okay. So this lattice spacing is greater than this interplanar spacing. I shouldn't say lattice. This interplanar spacing is different than this interplanar spacing. And as the Miller indices increase, the interplanar spacing gets smaller. Okay? So for cubic crystallites, we have A over the square root of h squared plus k squared plus l squared. That's the definition. That's just for cubics. For non-cubics, you have this definition. Right? But we can work in cubics, that's fine. And D is this interplanar spacing. When we talk about diffraction, a lot of times we'll work in reciprocal space. I don't know if somebody's going to cover reciprocal space. But the reason we do that then is if we have lattice spots, or we have spots in TEM that we're observing, then we'll see one spot that's a 010. If we move to the next spot, it's an 020. If we move to the next spot, it's 030. So that spacing gets larger. But the interplanar spacing is actually smaller. So we're in reciprocal space, so it goes larger. Okay? Good. Okay.
I have one question. Please.
Yes, ma'am.
In the previous slide,
Mhm.
how you can how to differentiate between high index plane
Mm.
What does it mean?
Okay.
High index and low index.
Yeah. To me, I just take the sum of h squared plus k squared plus l squared, and that value tells me high or low if that number's low. Now, is it you know, is the number 4 and lower low and the number 5 and above high? I don't have a specific definition like that, but that's what defines the value. So h squared plus k squared plus l squared.
So it's relative. It is higher than this or lower
Right.
than this.
Right.
And the summation of the HK, the square of the HK.
Yes.
Okay.
Yes, exactly. Okay. So the question was just about determining, just for online, because I'm sure that you don't have a mic. So the question was just about determining what's high,
High index and low index.
yeah, what's a high index plane versus a low index plane. Okay, so that's what h squared plus k squared plus l squared tells you. Is this a high value or a low value? Okay.
Thank you.
Good, thank you. Okay, so the bandwidth to the electron backscatter diffraction pattern is going to be inversely proportional to the d spacing. So if you look at a very high quality pattern like this one, sometimes you'll see different bands in here that are all parallel to each other. Okay. Now these aren't direct bands, these are little hyperbola, but you know, we consider them as just bands. And if you look at this one that's on the inside, this is going to be a 111 type of a band. If you look at the next one out, it's going to be 222. The next one's going to be 333. Right? So you'll see how these get larger and larger as the index becomes larger, right? And the d spacing is getting smaller. So 333 d spacing is smaller than 111 d spacing, but the bands are larger. And you'll see this in X-ray diffraction. You know, the low index planes are over at a small angle of 2 theta, whereas the high index planes are at high angles of 2 theta. See it in TEM, what's close to the zone axis or not. Okay, speaking of zone axes. A zone axis is defined only as the line of intersection between two planes. Okay, that's what a zone axis is. Now we call this a zone rule and a zone law, but really this is just a cross product, right? If you want to know the direction of intersection between two planes, you take the cross product of the normal of those planes, it gets you a mutual orthogonal third direction, and that's all this is, right? That's all this is. It's just the cross product. And then we say the Weiss zone law, which says if we take the zone axis direction and dot it with any of the planes that comprise that, it should be 0, right? The dot product just gives us the sign of the angle. If it's 90 degrees, we're going to have 0, okay? All right, so in these EBSD patterns, any place you see these bands that get these positions of intercept, these are zone axes. Okay, so these are directions in a crystal. Now cubics have this nice property that a direction is exactly aligned with the normal to a plane. So a 111 direction is aligned with the normal to the 111 plane. If you're not talking about cubic, that doesn't apply. Okay? So only for cubics it applies. So that's another good reason to only ever study cubic materials. Right? Just joking, of course, but it makes things much easier. And it's intuitive as we think about it. All right, so talking about crystal systems, we need to define all 7 of our crystal systems. So here they are in definition. These are the lattice parameters, and you'll have access to all these slides, of course. So cubic A equal B equal C, alpha, beta, gamma are all 90 degrees. For triclinic, A, B, C don't equal each other, and alpha, beta, gamma don't equal each other, and they aren't 90 degrees, right? So definition. If we are talking about texture, we have to rotate an orthonormal coordinate frame into coincidence with another orthonormal coordinate frame. We have a problem because only cubics have an orthonormal coordinate frame. So we have to transform all of our structures into an orthonormal frame. So that's what this equation does. This is just a transformation matrix that will take your ABC alpha, beta, gamma parameters, transform them into a orthonormal frame. And you can think of you can do this on your own, right? You take C and you define that as your unit, and then you take some other value of whatever your B was, take B cross C, make an orthogonal, take that value as your next one, and then take your old C with your new vector that you have, cross that, you get the other one, and then you'll have this transformation matrix, right? So to do it in a thought experiment is easy. This is what the mathematics is without deriving anything. And you'll see this in most crystallography textbooks. And then you have to say, how do I affix this onto my crystal? Right? How do I take this new orthonormal frame and put it on there? And for us metallurgists, the only problem comes in hexagonal. You have to be a little careful because some people will everybody puts the Z aligned with the C axis, but then you have a question for the X and Y. You have a question, should this go along 1 bar 1 0 0 or should it go along 1 1 bar 2 0, right? And if you look at EBSD software, if you look at the EDAX software, it does it that way. 1 bar 1 0 0 is aligned with X. If you look at the Oxford software, it does it the other way, right? So there's a 30-degree rotation between those two softwares that's not explained anywhere, really. I mean, there's people that have written about it, but you take the data, the orientation data, and they're just rotated by 30 degrees from each other. So you got to be careful with that. All right, symmetries is another important thing when we're talking about crystallography, especially with texture analysis, because we're trying to figure out how to mathematically represent an orientation, right? We have a coordinate frame of the specimen and we're rotating it into the coordinate frame of the crystal. But which coordinate frame of the crystal do we rotate it to, right? So if we have a cube like this and we rotate it 90 degrees about any of the 100 axes, it looks exactly the same, right? Mathematically it's different, but it looks exactly the same. So there are 24 different ways we can rotate a cube mathematically, and they'll all look exactly the same. So these are called symmetry elements. And if you go to group theory, this is part of group theory. Right? These are the symmetry elements of the cubic or the octahedral symmetry group. And so you can define, if you have a threefold axis or 120 degrees, about a 1 1 1, and then you have 4 different 1 1 1s, right? Those are all symmetry groups. Okay. Same with hexagonal symmetry, right? You have a 6-fold axis or 2-fold axis. Sometimes you have mirror planes you have to worry about. So a lot of different symmetry elements that are in the crystals. And you just have to know about those because mathematically, as we start to calculate textures and preferred orientations, if you get one that's like rotated with respect to some specific direction, and then you get another one that's 90 degrees rotated about 100, and you're plotting those and calculating them separate, even though they're the exact same thing, then you're reducing the actual preferred orientation in your material. So you have to take account of all the symmetries. Okay. All right, in crystallography, there's 32 point groups, right? So this depends on the centering. So we can have a cubic crystal symmetry, we can have it primitive, we can have it body-centered, or we can have it face-centered, right? And we can do the same with a lot of the other types of crystal systems, so you have to take care of those. Those different points are important as you're defining diffraction, and as you're defining the primitive unit cells that you can use to calculate the reciprocal lattice. Okay, because that requires only 1 point per primitive unit cell. All right, so here's point groups and just showing some of the different rotations and how the diffraction pattern looks exactly the same, right? So here's a 211 axis, here's a 112 axis, here's a 121 axis. They're all exactly the same thing. Right? We could call them all 211 or 2 bar 11, whatever we want to call them, we could call them all the same thing. They're all symmetrically equivalent. All right, space groups, there's 230, and they include all kinds of other things. And if you listen to the group theory people and the mathematicians, there's way more ways to define screw axes and inversions and translations and all those things, that even more than this 230 now. So a lot of ways. The important thing, though, is the symmetry is always seen in the diffraction. So we have to represent it in our mathematics, and we have to be aware of it in the patterns that we look at. So this is just showing some symmetry, 111 axis in the center. This is a threefold axis. So this band is going to be equivalent to this band, which is going to be equivalent to this band. And then we have mirror planes. That's what these three things are, mirror planes. This is a 60-degree rotation, a 90-degree rotation. All of those can be seen in the diffraction patterns. Okay. When we look at EBSD patterns, typically we have the specimen tilted. We have sometimes the phosphor screen is tilted, right? And so you don't always see the symmetry obvious. So for example, this little triangle here should look the same as this triangle, just a mirror across this green plane. And it should look the same as this triangle, which should look the same as this one, right? So this triangle should look the same as this one, which it doesn't, right? And that's because you have this projection that distorts your pattern, and you have this geometry that you have to deal with. So typically we don't see this nice kind of symmetric pattern. You usually see some kind of distortion. It's called a gnomic projection, G-N-O-M-I-C, a gnomic projection. So you see the distortion. All right, so I'll stop for just a second. I think I have 15 minutes, is that true? Do you know what the schedule is? I have till 11:15.
We started a little late, so maybe you can take some more time.
But we should be mostly on schedule. I think we should keep mostly on schedule.
You have 1 hour.
Because I think Setyam's talking next, right? So we have to show him some respect. So he says, what's on the schedule? Is it 11 or is it 11:15? 11? Okay.
But we started late, so.
Yeah, we started late, but it's okay. So I'm just going to go.
Some time, right? He can take some more time.
Yes, ma'am. Sure. 15 minutes.
15 minutes?
I'm going to take maybe 5 minutes more.
No, you can take 10, 15 minutes, no problem.
I'm gonna try and show some respect, so I'll show five, maybe 10 minutes. I have a lot of slides here still.
You are allowed to take 15 minutes.
Thank you. You're very kind. Thank you. Okay. So this is basics of diffraction, Bragg's law. This is what you'll see in a theta 2 theta scan with X-ray diffraction. And again, you'll see these low index zones are down here on the left and the higher index here. If you take h squared plus k squared plus l squared, right, this is 3, this is 4, right? So this is lower index than this one. And these determine, help determine what your lattice spacing is. This is just measuring pole figures. We're going to skip that because I want to get to this. So when we're doing EBSD, you shoot the beam into the specimen. Things start to scatter out, right? You get channeling. You get essentially inside your material, you have a source of electrons where the direction of the electron flight is everywhere, right? So the electrons are coming out in all different directions. They're not uniformly coming out in all directions, but they're coming out in all directions. And so as they come out as this red line, which indicates some electron, as it comes out, it happens to satisfy Bragg's law for a specific plane, then it will diffract and come out here. Kikuchi called these deficient lines. Another one coming from the other side, come here, that's an excess line, right? The angle between this becomes 2 theta. That 2 theta angle is what defines the width of your patterns. So as you get scattering, here's all the lattice planes. The exact geometric projection of this is the bisecting line between these two hyperbola that form on the phosphor screen. So they come in, they're bouncing out all different directions, right? Not just in a plane like was shown, whoops, on this one. It's not just the plane, it's all different directions coming out at the same angle. So if we have diffraction, beam comes in, diffracts, this blue line is the geometric projection of the diffracting plane. This is the excess and deficient lines. And when we look at the EBSD pattern, you can kind of see, like this band has a smaller width than it does out here, right? That's because these aren't exactly parallel lines, these are cones. And then this width depends on that 2 theta angle. Now, if we change the voltage, right, we have Planck's law here, where you use Planck's constant, and we say the wavelength is proportional to the energy through Planck's constant. So this is the exact same, this is a pattern from the exact same spot on the crystal, right? So this zone axis is the same as this zone axis. This one up here is the same as this one up here, right? It's just this one was taken at 50 keV, this one was taken at 10 keV, right? So lower energy on this one, higher energy on this one, and we get a difference in what the pattern looks like. So if we're trying to measure D-spacing, we would have a little better chance here. We can't really measure D-spacing anyway. It's very difficult to do that. Indra Samajdar will tell you that if you use machine learning, then maybe you can measure D-spacing, right? So he promises me that work's being published soon, so we're looking forward to that one. But he says maybe we can measure D-spacing, but I tell people in general, D-spacing, let's not measure D-spacing with. We can do relative D-spacings, but to measure exact, like if we're trying to measure strain based on that D-spacing, 0.2% strain, right? 0.2% is the standard definition for yield strains, right? We can't measure 0.2% difference, not a prayer. Because we have maybe 1,000 pixels in our image, a band will have maybe 50 pixels across. So if it's 1 pixel difference, that's already 2%, right? So if we can measure to within 1 pixel, that's 2% strain. But if we use machine learning, maybe we'll see how that comes out. Okay, and then not all planes diffract, so we use the structure factor. Yeah, please.
So for this texture studies, shall we take this EBSD always at higher voltages?
So the question is, if we're doing EBSD for texture studies, do we always use higher voltages? And that is really dependent. If you do higher voltage and higher current, you're going to get better contrast of your EBSD patterns, so you get better quality of data, right, in general. The problem is you get a much larger information volume. And so if you have a lot of defects, sometimes the patterns go away. So sometimes you decrease the voltage, maybe decrease the current as well. You'll have less contrast in your image, but sometimes you'll see images where you wouldn't see them otherwise. Okay, so for very highly deformed materials, maybe that's not true. Or very fine grained materials, right? So you have to be careful for yours, yeah, for your specific application. Okay, so structure factor, I'm assuming that we know some of this, but basically we come up with what we call selection rules. So if we have a body center cubic, H plus K plus L has to all be even. If we have face centered, HKL all have to be odd or they all have to be even. Right? If we have a 120, we won't get diffraction. So that's when you see pole figures, a lot of times you'll see a 200 pole figure, but you won't see a 100 pole figure, right? Because 100 doesn't diffract in FCC, right? Because we have an odd with 2 evens. But 200 diffracts. Geometrically, it's equivalent. It's the same to show 100 or a 200, so it's not incorrect to say 100. But your X-ray friends will be upset if you show a 100 pole figure. They say, yeah, there's no refraction. You can't do that. Okay, good. I made it through the last one. Any final questions before we wrap up this part? Yeah, please.
So, you were saying that higher voltage or higher current will give us better contrast, means better information. But that means that my interaction volume at very high voltage will be way higher. So if I want to maybe study only the top layer of the sample, then I will precisely go for maybe low voltage.
Yes, so he's just clarifying. The question is just to clarify that if there is high voltage, you have a larger information volume. And if you want to study something that's surface sensitive or just look at the surface layers, you don't want the high voltage, you want the lower voltages, right? That's the question, that's the point. And that's exactly correct, yes. Yes. Anybody else? We actually have a new system in our lab called we have a direct electron detector. So we don't have a camera on the back of a phosphor screen. We don't have a phosphor screen in that unit. It's only a direct electron detector, so the electrons come in and hit that. And we can get EBSD patterns down to 3 keV. So if we use 3 voltage of accelerating potential to 3 keV, we can get good patterns. And that is great for materials that are non-conductive, for ceramics, or for very small grain materials, right? Yeah.
The materials are not conductive. They can also show reflection.
Okay, say the question again so everybody can hear.
No, sorry, my question was actually the materials which are non-conductive, they will show reflection.
So the question is, if there's a non-conductive material, it's still going to diffract? As long as it's crystallographic, it will still diffract.
For reflection, scattering is required because the electron has to scatter.
Speaking mic now.
For reflection to occur, scattering is required by the electrons. The beam of the electron should scatter.
Yeah, so not only scattered, but diffracted, right? So scattering and diffracting aren't necessarily the same thing. So, but they definitely have to have some diffraction, some coherent Bragg diffraction, okay? And as long as that happens, so typically if we've worked with non-conductive materials, we have to coat the thing with some carbon or some gold or something, and that interferes with the diffraction, right? Because you have to shoot through the coating layer.
Okay.
And otherwise, you shoot the beam into the material. If it's a high voltage, you get this charge buildup, and you can't see the diffraction. You can't get good quality.
So the coating layer should be, what should be the thickness of coating layer? Means
Okay, so now the question is, assuming you're doing a coating layer, what should be the thickness?
yes.
So usually I will say use carbon, not gold,
Okay.
right? Use a low Z number,
Okay.
right? Carbon is best. And if you can get away with 30 angstroms, that would be wonderful.
Okay.
If you have to go to 50 angstroms or 100 angstroms, you can live with that. But the more you get, then the lower quality of diffraction you have.
Okay. So
Because the signal's coming in,
Mhm.
it will scatter it a little bit.
Okay.
Your Kikuchi pattern's coming out.
Okay.
It has to go through this amorphous layer, and it's also diffusing the signal.
Okay. So thinner coating is more better. Okay.
Thinner and low Z number is always best for coating. Yes. Okay, any other? I see another one.
So can you tell the difference once again of that, the difference between EDAX and Oxford one for the HCP crystals?
So this is on hexagonal crystals. So when you affix, I don't know if I can go back to that, but when you affix the orthonormal coordinate frame, you have a C-axis, and then you have a choice if your x-axis goes along 1, bar 2, O, or 1, bar 1, O, O, right? And EDAX chose to put the x-axis along 1, bar 1, O, O, and Oxford chose to put it along 1, bar 2, O. Okay, so that x-axis has a different meaning based on whether you're using that formulation of affixing the coordinate frame or the other formulation. And so when you are comparing the data between EDAX and Oxford, there's this 30-degree rotation. Not in cubics, but in hexagonals. Okay. It's just the 1 bar 1 0 is 90 degrees away from the 1 bar 2 0, right? So you have a choice when you put that coordinate frame down. Okay. Is X going to be aligned with one and Y with the other, or is it the other way? Right? And that's just a 30-degree rotation, right? So you just choose which one you want. And the two main, if I can say that, Brooker would be upset with me and Thermo would be upset with me. But those two maybe kind of historic companies chose different conventions. I don't even know what Brooker convention is, or Thermo.
So this will, so suppose if we do in one instrument and analyze in the Oxford, let's say we do in the actually there if we do EBSD, let's say in the there's a one is I'm forgetting the name, what is the EBSD company, and analyze in the Oxford because Oxford software.
Yeah, so if you take data and collect data with one software and analyze with the other one, it will be a 30-degree difference.
Yeah, okay,
what
there
it
is a
should be.
30-degree difference. Okay.
Yep. And if you use MATLAB, if you use MTEX to analyze the data, it lets you choose what your convention is. Right? You put that in. The other EBSD suppliers, it's hidden in the software. But MTEX will let you define what you want. Okay, good. Thank you for all the questions. Thank you for the discussion.
Hello, testing. Hello. Hello. Thank you, Professor Field, for giving this wonderful lecture. Thank you, Professor Field, for this wonderful lecture. I would ask Professor Shampa Madam to felicitate Professor Field with a small gift. A memento. It's not a memento, it's a gift.
I was just telling him that it was a very nice lecture, especially for student. He explained so nicely, simply and lucidly. So it was very easy to understand. That's what I think. And thank you very much for this nice presentation in this morning. We have learned a lot, right?
Thank you. So we'll have a tea break for 10 minutes. And then we'll be back where Professor Satyam Shuas from ISC Bangalore will be giving a lecture.
Check 1 2 3. Hello, hello. Hello, hello. Hello. Hello, hello. Hello, 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 hello. Check. Hello, hello, hello. Hello, hello. Check, check. Hello, hello, hello. Hello, hello. Hello, hello, hello. Hello, 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 hello. Hello, check. Hello, 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 hello. Hello, check. Hello, check. Hello. Hello, hello. हेलो चेक 1 2 3 हेलो 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 ठीक है इतना तो सफिशेंट है उसको करेंगे ये वाला हो गया एक नंबर हो गया अब एक नंबर को हेलो चेक चेक कैसा है ये हेलो चेक चेक हेलो हेलो उधर पीछे चले जाओ थोड़ा सा आगे जाओ थोड़ा ज़्यादा है तो मैं कम करूँगा चेक 1 2 3 चेक 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 1 2 3 4 5 ठीक है ये हेलो चेक 1 2 3 हेलो 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 चेक 1 2 3 4 हेलो 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 चेक 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 ठीक है ना माइक 1 चेक 1 2 3 यहाँ पे मत ये स्पीकर सामने है तो पीछे जा चेक 1 2 3 चेक 1 2 3 चेक 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 1 2 3
So, good morning again, and this is our second session. And before we start our session, I would like to request you one thing, that I have received a small complaint. It's a small one. A sound of murmuring is coming from behind. Okay, so I would request the students to not to talk during the presentation, because this is a soundproof room, right? So what happens that when sound comes from this direction and you are talking in that direction, it cancels the sound, and then some people may not be able to hear it. So I request a small presentations. We are accustomed to 2 hours of class. Okay. So professor is joining. Yes. So good afternoon, Professor Suhas.
Yeah,
This
good
is
afternoon.
Shomjit.
Am I audible?
Yes, yes,
Yeah,
yes.
good.
So before you say something, let me introduce you. So Professor Satyam Suhas is a renowned professor in Indian Institute of Science, Bangalore, and he is basically now the Dean of Mechanical Sciences too. He has a lot of pioneering work on the field of mechanical and physical metallurgy, specifically related to crystallographic texture. He has presented our country throughout the world. He has represented like an ambassador to the world, to our country, and we are really proud of him. I am also very proud to say that I am his first PhD scholar. I graduated in 2010 under him. So welcome, Professor Satyam Suhas. Welcome, sir. And
Thank you. Thank you.
and we have a good
Professor Shomjit.
amount of audience. Most of them are research scholar and
Right.
in MTech, and few of them are doing BTech in engineering. So this dice is yours, and
Right.
please.
I saw Professor David Field also in the audience.
Yes, he is there sitting in the audience.
Right.
Yes.
Hi,
Yes.
Dave. Nice. Great. So I will just share my slides. So let me see. Share screen. Yeah.
So I am leaving this dice. It is
Right.
to you now.
Right.
Thank you.
Right. Share screen. Share. So now I think my screen must be shared completely, right? My screen is shared,
Yes, it is. Yes, it is.
right? It is clear. Okay. So
It is clear.
thank you, Professor Biswas, and I'm very happy to talk to all of you in this workshop, SPARC workshop, and I am, as suggested by Professor Biswas, I am supposed to talk about representation of texture by pole figure and 3D texture analysis.
Sir,
So I will be talking mainly on these things. It's like a teaching mode seminar. So I think this is mainly for students to learn. That's what was intended for probably. So
may I say something?
please.
One second. So the first lesson of texture that I had is from Professor Satyam Suhas. So he is the one who introduced me to texture.
Thank you.
That's
Thank
it.
you for remembering this. So let's go ahead. So I think texture has been introduced to everyone by Professor Field. I think everyone knows about texture. So am I right? Am I right? Professor Field has introduced about texture, right? Hello.
Yes, sir.
Yeah. So Professor Field has introduced about texture. Hello.
Yes, sir. Yes, sir.
So I can go ahead with the further lessons. So basically, in pole figures, what I'm supposed to talk about, an important concept is a stereographic projection. And a stereographic projection is basically mapping of crystallographic planes and directions in a convenient and straightforward manner. It's basically a two-dimensional drawing of three-dimensional data, because in texture what we deal with is grain orientation primarily, and generally grains are three-dimensional in nature, right? We have planes, we have directions, and what we do with it is we present these directions and planes on two-dimensional plane, two-dimensional projection. So in this method of representation, planes are plotted as great circle lines and directions are plotted as points. Sometimes the planes, for our convenience, we indicate by the normal to the plane. That becomes a point, because then it becomes a direction, right? So what, by other than representation, representing the planes and directions, what we do is we learn the geometrical correspondence between crystallographic planes and directions with their stereographic projection. And basically, we also know about the important crystallographic direction that lie in a particular plane of a crystal. So these are basic things about a stereographic projection. And from a stereographic projection is closely related concept of pole figure. But before we go to pole figure, we should understand what is pole. So basically, here in this diagram shown here, we can see that there is a crystal placed at the center of a sphere, right? So let's consider a big sphere and put a crystal at the center of the sphere and draw normal to the plane. So normally it will hit somewhere on the surface of the sphere. If there is a cuboidal body or cubic body at the center of a sphere and you draw a normal to it, it will hit somewhere at the surface of the sphere, right? And here these are considered as poles, but actually I will show you that in actual projection, in what we do is we try to join these poles to the other side of the hemisphere, and then the line that passes through it becomes actually representative of that plane. So we go to this representation. Now, since in texture we are dealing with basically a polycrystalline material, and you can see here that these are the grains here. These are the grains of a polycrystalline material, a microstructure that most of us are familiar with. And we know that each grain is a single crystal in itself, and single crystal means close to single crystal. And this single crystal has close packing of atoms or lattice points in it, right? So this, for example, this is represented for FCC structure, and approximately this grain structure or this distribution of this lattice points or atoms in this case for FCC metal, then in this case you will see that these are the points of a lattice plane. Now you just see that, you just imagine that this is extracted from a grain, and let us put this sphere that I have just mentioned beside here where I am showing my pointer, and there are directions indicated as per the directions of this body or the sheet, whatever from where we are going to represent each orientation from. So this is the longer direction, rolling direction. So this is here, this is transverse direction, and this is the normal direction, normal to the sheet plane or normal to the plate. Now you see what we are going to do is, from this combination of lattice points, we construct a unit cell, because this is basically composed of lots of unit cells together. So we have a unit cell here, that is one unit cell that represents the FCC unit cell, right? So now next step is we consider that unit cell that just join the center of those spheres, and then it actually becomes a unit cell. Now this unit cell you transfer at the center of this sphere, right? So this is exactly the same. So basically what we are seeing here, we are going to map here in this sphere. So you see this unit cell is placed here. Now what we do is we try to draw, as I mentioned, that for getting poles, we have to draw normal to each of the plane faces. So this unit cell has these three. Right now we are going to represent, it's an infinite number of planes, but we have, let's see, three simpler cases. So we have three planes, 103, 100 type of planes, that is 001, 100 and 010. These three planes are there. So this is exactly same oriented as in the material, right? In the same condition as it is similarly positioned with respect to this RD, TD and ND as shown here, and similarly placed here as shown here. Now what we do is we just draw a perpendicular normal to these planes, which is touching. Now in this sphere, it is not showing that it is touching the inner surface. It is not terminating before. It is touching the inner surface because it's a sphere. So you can see that this is just produced to touch the sphere surface. And so these touching points on the sphere inner surface of these normals drawn on the plane, let us mark as 1, 2 and 3. Let's see only these three planes. Now what we do is we join, since the sphere has two parts. Normally if we compare it with a globe, we call it the top one we call as North Pole and the bottom one we call as the South Pole. So suppose these normals are touching the sphere in the northern hemisphere of this construction, then you join these touching points with the South Pole. So basically this 1, 2 and 3, you just connect it to the South Pole, right? So now you will see that there is a line passing through this diametrical circle, which is also a great circle of this sphere. It is passing through this and while joining this South Pole. So similarly you can see here and similarly you can see here. So now these lines, the point at which they pass through this circle are highlighted here. So for example, for the first plane, when it is touching at point 1, if you join this with the South Pole, this point, then it passes through 1 prime. Then similarly for the plane 2, it is touching here at point 2 and it is joined to South Pole. It passes through this circle, the diametrical circle at 2 prime point. Similarly for 3. So we have 1, 2 and 3 points which we obtained by joining these touching points of this normal on the sphere that we have constructed around this crystal or around the sample, whatever you call, right? Now you just cut this circle out of this sphere and just put it on the piece of paper. So just I have extracted it and put on the piece of this paper, right? Now it is just 90-degree rotated and then it is here. So here you will see that this point, that 3 prime point is here, 2 prime point is here, and 1 prime point is here, like this point is here. So these 3 points are basically, what are these 3 points? They are basically representing these 3 planes, 1, 2, 3, on which we have drawn the normals, right? So they are there. So basically the angular relationship between these 3 points is same as the angular relationship between these planes. This plane, and this plane. So these are now, what we have done is one plane, which is a 2-dimensional construction, we have converted to one point. So a plane has been converted to one point. Once it is a point, we can easily represent this on a two-dimensional plane or a piece of paper or on a screen. So as you see that these 3 points represent these 3 planes. Now we can do the same thing with each of these crystals. So if we go back, you have so many grains. Similarly, so many unit cells are there, and each one you can bring it here at the surface at this, and then again you can have each plane over there, how these planes are oriented, and then you can do a similar procedure, and then you can get lots of points. So for example, so if you just put this crystal in a cubic manner, like for example, you just make it perfectly aligned with RD, TD and ND, then you get this projection or these points as center as 0, 0, 1, and then there are other relative disposition of other planes. So in the previous exercise, I have just shown 1, 0, 0 type of planes, but you can do the same thing with other planes like 2, 1, 1, 2, 2 type of plane, 1, 0 type of plane, 1, 1, 1 type of plane. So all that you can see here, and you will have several points that represents the orientation of those planes with respect to your reference frame, right? Here reference frame has not been incorporated, so just it is showing the stereographic projection on a plane. Now, one thing you have to understand that what we have done is in this exercise, we have projected, the projection plane is this, and these points are disposed with respect to this, the plane which is parallel to ND, right? Plane which is parallel to the plane normal which is parallel to ND, or plane which is normal to ND. This is disposed as per that. Now similarly, we can also do a projection from the side, right? You can also look from the side and then you can do this projection. So that way you can keep changing the projection. So if you project the whole thing on 110 plane or 111 plane, these 3 are important planes in the diffraction of FCC metals and alloys. 110 comes as 220, and so these are the 3 important planes, and you will see that the relative disposition of these points indicate where these plane normals are located, or where are these planes located. For example, if you have 111 as a projection plane, then from 111 to 211, what is the angular relationship? So always remember, a stereographic projection is an angle true projection. It's not an area true projection. And you can see that, for example, this plane we can see 111 and 0, 1 bar 1. So you will see that this whole distance is 90 degree. So the angular relationship between this and this is 90 degree. Similarly, this plane and this 10 bar 1. So similarly, there will be some angle between. If you measure the angle, you can put wolf net and you can see the angle between this plane and this plane. So you can get angular relationship between the planes. And if you have some of these points representing sample geometry, then you can tell about all the crystal planes or all the planes in your polycrystalline materials, how they are oriented with respect to specimen frame of reference. So these 3 things are basically same, but only the way we are looking at. For example, if you have a body, a physical body like this mobile phone, if it is seen in your screen, in your projection, so you can look from the top, you can look from the side, or you can look from the bottom, or you can look from angular way also. The views will be, the mobile phone will be the mobile phone, the whole structure will be the same. Only thing, the way you are looking at, that gives you different type of disposition of these planes. So this is the projection of the different projections of the same crystal. Now, what we do in pole figure, we do the same projection as here. You could see here, this is 100 type of projection here. So we get, this is a stereogram, but later, suppose for example, if we are projecting this with specimen frame of reference embedded to it, and some of these planes for a polycrystalline material, all these planes which are oriented differently, they are somewhere represented. Now these intensities require you explanation of how this come from. That probably will be in the next lecture by Professor Suresh, who will tell you X-ray diffraction, origin of these intensities. But here I am just telling you that all these orientations of planes can be concentrated at one location, and you will get some strong points. These points represent, now you can see how these are crystallographically located. Like suppose this is a 100 projection, right? 100 projection, and these are the 4 points that we are seeing. So in 100 projection, you will see that these 4 are located as 111. These are 4 111 planes, right? The way I am moving my pointer. So these are basically 111 reflections. So this is a 100 stereographic projection where obviously the ND or the projection plane is 001, but with respect to 001, 111 is appearing here. So you can say that this has the center, which is ND is parallel to 001 and RD is whatever it is here. So this can be, this is also 001 here. So you can have, that way you can identify orientations in a pole figure. What happens in a polycrystalline material, as you will see here, there will be several grains and each grain is having a different orientation. So these will give rise to a cluster of points all through spread all through the pole figure, and also these are related to the specimen frame of reference through a certain relationship which you will learn when you are explained about the measurement of X-ray, measurement of pole figures. You will realize, and these are the orientations which are closer to this specific orientation, like 001, 100, 010, and you can get these clusters of orientation. And what happens, you can join them, all iso intensity contours can join, and they form like what we see the pole concentrates or contours. Contour lines represent the intensities. Central one becomes obviously the most intense because this is the most ideal location of the orientation, right? So as I mentioned that you from this representation you can mask other projections from appearing, right? This is done in your experiments where you are orienting your crystal or your sample with respect to a specific Bragg angle. So you can choose one Bragg angle or one orientation, and then same orientation, same crystal orientation can manifest in 2 ways, right? So you can see here, right? So for example, if you want to project only 010, then you can have these planes, others will not appear. Then if you want to project only 110, then only 110 type of planes will come, others will not appear, right? And so, for example, now how do these pole figure represents, how do they relate to the actual crystal? You could see here, this is the sheet or the plate with, for example, this is the crystal here, right? This, you can easily see that this crystal is, you can see that as if a Rubik cube or any cubical object is put on a sheet, right? But it is not exactly aligned with this axis. It is slightly tilted. It's diagonally aligned with the rolling direction. The face diagonally aligned with the rolling direction. And the plane, the top plane is parallel to the sheet plane. So if you project this on 100 pole figure, you will have this disposition of points where RD is here. RD is along 11. RD is along 110, right? This is the direction, 110 direction, and you will see that this normal is 001. So and so you can project this orientation in three ways or multiple ways. So here three important pole figures are shown. So if you project this same crystal into 111 pole figure, you will have this disposition of points, that is intensities. If you put at 111 pole figure, you will have a different disposition of intensities, and if you put 110 pole figure, you have multiple appearance of points. But all these three mean the same. If suppose somebody is expert in analyzing this pole figure, he will also analyze and say, hey, this material has this kind of grains. Primarily this kind of orientation is present in the material, or most of the crystallites or most of the grains are having this kind of crystal orientation. Right. So now there are two extreme cases. If there are all crystals, ideally, this is a very ideal situation. They are all scattered in different direction. All are having very different orientations. Then you will have basically any projection that you take, it will have a random distribution of, based on the random orientation of these crystals, you will have random distribution of points. Right? If your material is fully textured, right, as it is shown here, fully textured means within the limits of misorientation, then you will have a completely concentrated points at one location, and as you will see that here it is very strong, like 4,000 is the intensity. So 4,000, so that means 4,000 type crystallites, or the intensity is 4,000 times as if there is a random distribution of points over there. So that way you can see by such kind of diagrams will appear, and this is the outcome of X-ray diffraction based experiments. You can also do it by electron diffraction, and then you can say that, okay, if this has appeared, that means the crystallites may be distributed like this. If this has appeared, then the crystallites are distributed like this. And there could be an intermediate situation. Now, how do you index the pole figure? That is probably one of the things which I was supposed to do. So for example, once you measure a pole figure for a polycrystalline material, it is somewhat like this, as probably it is appearing in your screen, that 4 concentrated points, because I have been showing only similar kind of pole figures from the beginning of my presentation. And if suppose someone says that I am giving you this pole figure, please tell me what is the orientation. Then here, first of all, the first question you have to ask, which pole figure is this? Means this was recorded using which type of Bragg angle, at what angle it was measured. The person says that it is 111. We have used all through 111 peak for measuring this pole figure. So this is, then you have to see where this 111 peaks are located, because if you are doing with 111 plane parallel to the sheet plane, that Bragg angle if you are using, then you will get only 111 orientation. This is because of exclusivity of the Bragg's law, because for Bragg's law is valid only for a particular plane at one given time because of the interplanar spacing and Bragg angle constraint. So now suppose I have to index it. What is this orientation exactly? Which plane is parallel to RD? Which plane is parallel to ND? Then I will just bring one stereographic projection. This is the simplest one I am showing you here. So this is the first one itself. Like first we take 001 projection, and I have just imposed on it. And then you will see that since this was 111 pole figure, so the locations of maximum intensity must be 111. So we easily saw that, yeah, these points are 111 points are located and they exactly match over here. So now in this case, what could be the orientation of the crystal or orientation of the sample is plane is parallel to, the center is at 001. So plane is parallel to 001 and the direction is 100. And probably by now you know that the texture components are represented by a combination of plane parallel to the sheet plane and direction aligned along the longer direction or rolling direction, This is for the sheet material. For other type of textures, there are different types of plane and direction consideration. But let's consider only the sheet plane or rolling texture, where you have the central plane is plane parallel to the sheet plane. So here it is 001, which is parallel to the sheet plane, and 100 is parallel to the rolling direction. So the texture component is 001, 100, right? So this is one indexing, and this is definitely the simplest possible orientation that I could get for you. But there are, in real life, you get complicated orientations. And then what you have to do is if the measured HKL pole figure does not, then you have to choose specific standard stereograms. Here, the way I have chosen standard stereogram 001, and in first shot itself, it got indexed. Sometimes in first shot, it doesn't get indexed. Then you have to choose multiple stereograms. You can superimpose it and see how all these 111 poles are getting indexed. So for example, in this case, if you can see that there are other methods where this ideal situation does not occur, then if the measured HKL pole figure does not have a region of high intensity at the center, then exclude the HKL projection and take any other projection to index the pole figure. Because this, if the central intensity is not there, that means that pole figure, that plane is not parallel to the sheet plane. So you have to go for another pole figure. So for example, this was 111 pole figure, but I started with 001. So it has matched. Suppose I would have started with 110, then it wouldn't have matched, right? The intensity distribution wouldn't have matched like this. Then sometimes what happens, your intensities are matching not just by superimposing. You have to rotate the projection in such a manner that the regions of high intensity is captured. Like in previous slide that I have shown, there is no rotation. But sometimes if you rotate the standard stereogram, then you will get the coincidence of all these regions of higher intensity, and then you can say that this is that clearly mentions about the plane and direction. Plane will always be plane parallel to the sheet plane, and that is the center of the stereogram, with help of which you are able to index it. But the direction will change after rotation. So your direction may be, instead of 001, it will be 110. So if suppose you have to rotate by 45 degree, and then you have to, then it coincides with all the high intensity points, then it will be 001, 110. So what the last set of Miller index represents the direction parallel to the direction parallel to the sheet direction, and the first set of Miller index indicates the plane parallel to the sheet plane. So this is the exercise that you do. I will leave these slides with Professor Biswas. He can circulate it if he wants. So similarly, you can have another texture component like 110001. You can have, if you read it through a 100 pole figure, then you will have the disposition of these points, right? It is like this. Same texture, same orientation can be presented on 111 pole figure, and then the disposition of poles will be different. And for 110 pole figure, it will be even more different, right? But actually, these are all single orientation pole figures, just drawn for easy explanation. In real life, the pole figures are very complicated. They have overlapping orientations, and it requires a lot of effort to understand or decode what all orientations these represent. So for example, this is 200 pole figure for 95% gold rolled 70-30 brass, alpha brass, and you will see that it has several pole figures, several orientations here, right? And one has to identify where are the centers. So these are the locations, and one can decode it. Normally, it is very difficult to do it by one pole figure. These days, it is easy because things have become automated. But earlier times when things, the orientation indexing was not automated, we used to use several stereograms and index the texture components. And also you have to record several pole figures for a more lucid explanation of or lucid identification of texture components. So this is all for cubic system. For hexagonal systems, for example, because I am just bringing in hexagonal system because most of the metals have either cubic or hexagonal crystal structure. So here there is subtle difference because of the 4-index system of the hexagon. You have to use double stereogram to index the texture components. So if your texture components are very similar, where the Miller indices of plane and the direction normal to direction parallel to it are same, then you have a very easy coincidence. Like you will see that 001 or 1 bar 20, 10 bar 10, all these orientations are present here. You can see. But if you have complex orientation, then you have to use one double stereogram where directions and planes are represented differently as shown here with the filled and with open circles. And then again you have to do the same exercise, one time by plane and one time for direction. You have to index. Now there is another thing that we use quite often is inverse pole figures. Actually, inverse pole figures are basically opposite to pole figure. In pole figures, we present crystal directions in specimen frame of reference, right? Because we already fixed the pole figure that the center is ND, one side is TD and top side is RD. And now we see how the crystal directions, crystal plane normals are aligned with respect to these 3 directions. So that is pole figure. Inverse pole figure is just opposite to that. There we fix the 3 reference systems like 111, 100, 110. These are the parts of a stereographic triangle. You can see this is again, you will recall the stereographic triangle. So each triangle has, you will see if you divide them into this 24, they will get divided into 24 triangle. It's not exact triangle sometimes because one side is curved because of it's not straight line here. So you will see, but each of these sections, there you will see that it will have 001 at one corner, 111 at one corner, and 101 at one corner. And it is assumed that any of these sections can sufficiently represent the specimen direction if you have only one specimen direction. For example, for wire drawing, what we represent is wire drawing axis. Or for extruded materials, we just present extrusion direction. Or for tensile test, when we are doing only tensile elongation direction. So we represent that, and that for that you don't need to have the full pole figure. You can represent as an inverse pole figure. You just take one section of the stereographic triangle and mark the direction. For example, this is the sample here, and you will see that here this is an ideal construction. It doesn't happen like this. Looks like a single crystal, but you could see that the wire drawing axis is aligned along 110 direction, right? Now, if I have to represent this orientation, I just take a standard triangle here and we present here 110, right? Here, mind it, this is not a pole figure, this is inverse pole figure. And what is presented here is 110, it is the wire axis. Because wire axis is aligning with 110, you get a maximum intensity here. So even though sometimes inverse pole figures are also represented at full stereographic projection, but the meaning is different, right? For example, this is also the same thing as this, right? But here you will see that there is no RD, TD, ND here. Just stereographic projection coordinates are there. And what is being presented here is this wire drawing axis, which is here, 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 here. So all these places, this is the wire drawing axis. So wire drawing axis means that what direction of the crystal is aligned with wire drawing axis. So this is what it is presented. And then you can see the unit triangles represent from 111 to 100 to 110. You can have gradual rotations. These are, I'm always explaining you with the ideal situations. In generally in classrooms, we give exercise for non-ideal situation where people learn, but this is enough for this lecture. So I think you can take it out from there. So now what happens for these situations, you get what is called fiber texture. So if you plot a pole figure, right? If you plot a pole figure, instead of a point, you will get a fiber. You get a continuous lines because you have the plane and there is one axis which is presented there. So this is actually RDTD is not there. This is you're presenting in a specimen frame of reference, and then you get a continuous line in place of, because here you can see that the one direction is fixed, but the planes are, you can see the planes are, some planes are coming towards me, some planes are going towards you, some planes are going in this direction. So that indicates this distribution of this kind. And you can present, if you are presenting on this plane or this plane or this plane, you can get a similar disposition of these orientations. Now, the later part, I think, well, I have some time, right? So now, later part is three-dimensional presentation. So, although I have been trying to impress upon you that pole figures represent the crystallographic texture in a very adequate manner, but there are some limitations. First of all, the description of textures by pole figures is incomplete. There is one measurement related issue that I am not bringing out at this point, because that will become obvious after you are taught about X-ray based measurement of pole figures, and then defocusing corrections and other things will come into picture. So that is one reason. But more important reason is there is no uniqueness of any orientation. For example, in this case, you can see the hexagon is situated there. If you rotate it by any angle alpha, this is inclined at an angle alpha. But if you rotate it in this manner, it will not lead to any change in the pole figure. But the textures are changing, right? The directions, relative directions will change. So this you cannot record in a pole figure so easily. And another more serious implication, this is also serious, but even more serious implication is, 2 points can be very close, but they may be substantially different orientations. So in principle, the resolution of the pole figure is very poor because the entire three-dimensional crystal data is presented on 2 dimensions. And you will see that how do you make the projection, it will depend on that. For example, if you just consider now from standing here, I cannot give you a better example. If the 2 trees are aligned to each other and you are making a projection from one side, from the side of the tree, you will see that the other tree will be almost overlapping with that. So the 2 things, or maybe if it is a little, and suppose you see the projection plane somewhere else, then it will appear as a 2 separate trees, right, from 90 degrees to each other. So it depends on how you are taking the projection, and that will decide the resolution of the pole figure. So similarly, here there are countable number of bodies, but in a polycrystalline material, there are countless number of crystals, countless number of grains or large number of grains. There you have to, and each grain participates in the diffraction. So therefore, you will get diffraction output from each one of them. So if there are such kind of ambiguity, then you will not be able to represent texture properly. So that means it indicates that projection methods are not the best ones, though they are the very good ones to give an initial indication of texture. So the best is to make a direct representation of texture. So for direct representation, how do you represent an orientation? If a body, if my cell phone is here, right? If this cell phone is parallel to, it is, you can say that it is inclined, if at all it is seen on your screen, if it is inclined, then you will see that this is because I am using this Cartesian frame of reference, that where x, y, and z directions are aligned as per the configuration of this room where I am sitting, right? But suppose the room is tilted, right? Then even though the cell placing of this phone is same, then it will look tilted, right? It will appear tilted even though it is same, because the observation is done from a different plane. So basically, there are to observe any orientation, we need three parameters, right? Three parameters of the crystallites, right, or any crystal, and three parameters for. So basically, you have enough number of parameters. For example, in this slide, you can see that this is a sheet, and this sheet is defined by these directions, right? So these are x, y, z directions, and then there is a crystal which is embedded here, which is a part of this sheet, and it has its three coordinates like crystal coordinates 0, 0, 1, 1, 0, 0, and 0, 1, 0 are inclined like this, but the crystal is not aligned along these crystallographic planes or directions are not aligned along the sheet directions or sheet frame of reference. So what we do is, suppose they are inclined, their 1, 0, 0 axis is at alpha degree to each alpha degree, beta degree. So likewise, the major crystallographic directions are some, and the planes are aligned in a different way. Then what you do is, to represent this orientation, you require a very large set of parameters. Like here, how do you choose crystal symmetry and crystal coordinates that I have given? But to represent this kind of orientation, what you do is, you need a crystal coordinate system and a sample coordinate system, and then there will be a rotation or orientation matrix that embodies the rotation of specimen coordinates into crystal coordinate system. And this matrix will have the first row as cosines of the angle from the first crystal axis with each of the three specimen axes. Similarly, the second row will have cosines of the angle between second crystal axis with each of the three other specimen axes, and the third will be for the third crystal axis. So what we'll do is, this makes it a very complicated thing, and it makes a nine element matrix, right? And so we have to determine all these 9 orientation matrices, and then that makes it very complicated. It's some kind of over determining the orientation of a crystal in a specimen frame of reference. This is just because we have left out the idea of doing projections. So this is over determining it. And so what we do is, generally we should have only 3 angles or 3 ways to represent it. So this is done by using the Euler angle representation, which was Euler has given a way to connect 2 frames of reference. It was done in 1800s, that 2 frames of reference by a certain mechanism of rotation. If you follow, then you will end up in having 3 angles, and these 3 angles will represent the relationship between the 2 frames of reference. So exactly that is what we need to do here. And here it is done by Euler angle method, and this is not a unique way. It can be done in multiple ways. So, but when this problem was proposed, some very intelligent people were working in this field, and one of them is Professor Hans Joachim Bunge from Clausthal. So Professor Bunge proposed a method, and almost at similar time in the United States, one Professor R.J. Rowe was there. He also proposed another method, but using Euler angle concept only, and probably around same time or maybe a little later, but not but independently, one Professor R.O. Williams from UK, he also had a method. But since texture is highly populated by German scientists from the beginning, whichever country you go, lots of German people will be working on texture, or at least the first or second generation people were all having some connection with Germany. So Bunge method got more popularized, and let us see how it works. So Bunge method involves 3 rotations. So for example, here you see there is a specimen frame of reference, ND, TD, and RD, and then you have the crystal frame of reference. Here I am not drawing the entire crystal, just the three axis, major axis of a cubic crystal is shown here, like 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And these three are the mutually perpendicular directions, right? So what we do is you rotate, give a first rotation as if you are having three sets of these coordinates and you are holding in hand and you are rotating. So the first rotation you give phi1 about the normal direction ND, so and transforming TD into another axis TD prime, right? So for example, here exactly same thing is put here, and in this circled region or this encircled region, you will see that there will be some rotation taking place. So what I do is first rotation phi1 about normal direction ND that transforms TD into TD prime. So around this direction I am going to rotate. So you see the first rotation, this kind of a rotation was given around this. So this, if you rotate this, then what after rotation, TD became TD prime and RD became RD prime, right? So this is what it is. So TD became TD prime and RD became RD prime. It came to a new position. Now you give a second rotation phi about RD prime, right? This is the new RD prime, second rotation, and this transforms ND into aligning with 0, 0, 1 direction, ND into ND prime, which aligns basically with 0, 0, 1 direction. So you can call it N prime or 0, 0, 1. And then of course this will not leave, because it's a rigid frame, it does not leave with other axis intact. It also rotates it to a second position, because we are now focusing on aligning this with this. So this leads to a second position that makes it to TD. So TD becomes TD prime becomes TD double prime. So let us see what is this rotation. So this rotation was what I mentioned, was around this this rotation was around ND, and the second rotation was around the transformed RD direction, which is here along the laser pointer that I am showing. So this is around this, you rotate it, and then it becomes RD becomes the ND in this, after this rotation, ND becomes aligned with 0, 0, 1. So now at least one axis is aligned. Now it's very simple, because again we take advantage of rigid frame. So you have to exercise a third rotation phi to around this ND or ND prime, whatever is the new ND or 0, 0, 1, you rotate it such that RD prime coincides with 1, 0, 0, and then TD automatically will coincide with 1, 1, 0. So let us do this rotation, but this rotation has to be around ND, the new ND or ND prime. So this is this direction. So I will say, yeah, so this is the rotation that you are giving. And if you do this, then you will see that all the axes are coincident. So now with these three rotations, phi1, the first was phi1, phi and phi2, these three rotations we have done, and this has led to coincidence of ND normal direction along 0, 0, 1, TD direction, TD along 0, 1, 0, and RD along 1, 0, 0. So basically we have made crystal frame and specimen frame coincident, right? And in this whole process, what was done, we have just used three angles, right? Phi1, phi and phi2. So that means a crystal which is located or embedded in a solid body, right, has a crystal axis, right? So now to describe its orientation, to give its address, right? Like for example, if suppose there is a person located in metallurgy department of IIT Kharagpur, right? So what will you say his location? That he or he is sitting in the office of metallurgy department of IIT Kharagpur. So you will say that, okay, he is 50 meters away from here in this direction, right? Right? And then you will see that, and he is in the second floor, then you will give he is say 10 feet above this, right? Or 2 meters 3 meters above in this direction. So that way, if you put three measurement parameters, you can exactly locate that person over there. And or maybe if suppose a person you can identify, but suppose a file is kept somewhere in the office and you want to say. So by these 3 parameters, you can exactly indicate the location of the file or orientation of the file. So similarly, a grain embedded in the body, its orientation can be described with respect to the specimen frame of reference by using 3 angles. So for example, if you have a sheet plane and you have see, I'll give you this example. This is again my phone, and this is the crystal. Assume that this is a cubic crystal. Now, if I am putting here, that means there is no rotation required, right? It's already 001 is aligned along with ND, and 010 TD, and other one is along RD. So in this case, the 51552 is 0. So for this orientation, which is the cube orientation, this is 51552 is 0. But suppose this crystal, I hope it is visible, it is rotated like this or like this, right? So it is at 45 degree. So you require not other 2 angles will be 0, but the rotation about ND will be 45 degree, right? So then to make it coincident with the specimen frame of reference. So this, the crystal which is located like this, it has its 51552 as 000, but this one has 4500, right? Because you require 1 rotation. Similarly, suppose some crystal is inclined to the specimen frame of reference, then you may have to give all 3 angles, 3 rotations to make it coincident with the specimen frame of reference. And this essentially leads to 3 angles representation. And this rotation, if you consider in terms of direction cosines, it will come as a 3 matrices, and the product of these 3 matrices gives you the total orientation matrix. This leave it with you. You can do your exercise. And so that means each crystal's HKL can be mapped with the specimen frame of reference with the help of these 3 angles. And so now each crystal has an address, or each grain has an address embedded in these 3 angles. So now let's forget about the crystal frame of reference and forget about specimen frame of reference. So now we have only these 3 points which tells about the relationship between crystal and specimen frame of reference. So the intelligent way is, now let us construct a orientation space with these 3 angles which we have derived as a result of these rotations, which are essentially, we are not rotating, catching the crystal, rotating to align along with the specimen frame of reference, but we assume that if this crystal is rotated through these 3 angles, the crystal will align along the specimen frame of reference. So those 3 angles are, if you construct, so if for a polycrystalline material, this is a 3-dimensional body, your axis becomes, instead of XYZ, it becomes 51552, and each point in this space is a set of 3 angles which represents a crystal. Now, since each crystal has a unique orientation, now what you do is you just represent these points. And so there is no question of ambiguity. If 2 crystals are of the same orientation, they will have common 51552. So this way you can have an orientation space and you can represent the crystal in a particular way through Bunge method. There are other methods also, as I mentioned, but I am not going to emphasize because I am almost close to my time. Right, so this is the way it is done. But now where is the orientation distribution function comes? So now that we have described the crystallites into by 3 angles, now if we have to represent them mathematically, how the distribution of those orientation is there in a specimen frame of reference, then sorry, in a orientation space, we need a mathematical connection between the 2, so that I can say that, for example, in a 3-dimensional space, suppose you have to say that some body is located at, say your fan is hanging at the ceiling. So you have to have a coordinate over there, and or you have to describe the motion of a body in a 3-dimensional thing. So you can describe the equation and you can say that at time t, this point is here, and at time t plus say 5, the point will be here. So the need is to find an equation which connects these orientations, and so that it can be handy for representing the texture. So the overall polycrystal mapping is done. So this can be done by two ways. So you can define a mathematical function called FG, which is ratio of orientation or volume fraction of crystallites with orientation G with respect to the total crystallographic orientation. So this is the way it can also be done by number, and both the ways you can correlate. And this FG is basically a spherical harmonic function, and this spherical harmonic function correlates G with FG. So FG gives you an equation, and if you plot this, this is since I don't have much time to go through this, so I will leave these slides with you, and you can read it. It's self-explanatory slides. So you can take it, and this mathematical function we plot in three-dimensional orientation space. And the data for this mathematical function comes again from X-ray pole figure measurements or EBSD-based pole figure measurements. And what if you plot them in three-dimensional space, you will some kind of this kind of a surfaces and structures. And then what you get here is a complex structure basically, and then you just make them into slices. This is much simplified structure, only peak points are represented here. And then what you do is so each peak corresponds to one 51552 angle, and then you identify that what location of 51552, because each 51552 is related to HKL UVW. So these maxima will relate to a specific crystallographic orientation. Here it is a general standard FCC orientations given. You can match it with this, or you can, for convenience, you can cut these sections, this three-dimensional body or this three-dimensional body, you can cut and spread on your sheet or on your screen or in your piece of paper, and then you can identify, okay, this is, for example, what is this maxima? This corresponds to say 45 degrees or 35 degrees of phi, and then 45 degrees of phi 2, and basically phi 1, and then you have phi 2 equals to 0. So you get some three set of angles, and then you can say that, okay, this is the brass orientation. And so therefore each orientation can be mapped in three-dimensional way. You don't have to reveal all the sections, rather a few important sections, because of symmetric nature of crystallographic phenomena. You can get only few sections where you can get all the orientations projected. There are standard charts where you can match and you can easily map the orientation, or it is possible to, these days you can just click it and get it on through softwares. So for example, if we have an orientation distribution function with these maxima, a section of 45 degree, I can easily correlate that, okay, this maxima is because there are orientations with 111 bar 1 bar 1 2, and this maxima is because of 111 1 bar 2 1. So if a person who understands texture, if you just give him this orientation distribution function, which comes by all the treatments that we have gone through, he can easily decode what is the crystal orientation. And then once you know about it, since to correlate the crystal orientation with properties of a polycrystalline material, you need this mathematical function. You cannot use each orientation in a discrete manner. So you need orientation distribution, so that if you are calculating the elastic moduli of a polycrystalline material, or you are calculating the strength of a polycrystalline material, then you can use this orientation distribution function, put into those relevant equations, and then you can get overall elastic modulus or properties of a polycrystalline material. And you can also reveal that what orientation is present by these contour lines. So I think this is what I was supposed to talk, and I think I have just dimensional representation. So I have to cover this much, but I think some of these things will be told to you again by Professor Suresh, who will be telling you about X-ray measurement of textures. So with this, I thank you all for your attention.
Oh, thank you, Professor. I think he has left already. So this session basically ends here. We would like to go for lunch now, and there are lunch coupons for you to go to TGS to lunch. But before that, if we would like to take a good, nice photograph. Yeah. So thank you. Thank you, Professor Suhas, for giving such a nice lecture on pole figure, understanding pole figure, and rotation of the Euler angles. And that was so. Can I see him?
Yeah, I can see you.
Yes. So. Can we see Professor Suhas? Yes.
Yeah.
So
yes. My camera is on.
Yes, they are maintaining, right. So thank you. It was a great pleasure that you you took my request and give this presentation to our students. We have a small kind of a memento for you, and we will send it to you, or I know that you are going to come to IIT Kharagpur in, I think, next 3 or 4 days, on 22nd, I suppose.
Right, yeah.
So we will present you with that memento to you. I'm so thankful to you, so grateful to you for giving us this lecture.
Thank you so much for inviting me and letting me talk to the students for this.
Thank you so much, sir.
If there are any doubts, all of you, if you are still around, those who are in Kharagpur, you can catch me when I am there. In Kharagpur, I will be reaching in the evening, in the afternoon of 21st, and leaving in the afternoon of 23rd.
So please catch him.
Sure.
Thank you, sir. So we will end this session now. Thank you so much.
Bye.
Bye. Take care, sir. So we'll go for the lunch now, and there are coupons. So you want to distribute the coupons now? Let them have photograph below, and then we will directly go. We can even walk together with the coupons. Mine like that. Okay.